Alright, welcome back to part 2 of our lecture about thermally driven flows. Now, remember I told you at the beginning of the first one that there's actually a number of different kind of examples of flow that is thermally driven, but we're going to stick with what your book chose to do, and that is focus on just two examples, namely the land sea breeze system that we did in part 1, and now the so-called anabatic and katabatic wind systems that we're going to observe when there are terrain features like mountain ranges and so on. This is going to be different than what we did in the orography section. In the orography section here, we were talking about wind that was being forced up or forced down mountains by like the large-scale flow. Now we're going to be talking about flow that freely goes up and down the mountains just due to buoyancy and so on. The word anabatic means that the flow is going up the mountain, and katabatic means that the flow is going down the mountain. It is the downslope wind. The problem with these terms, and to my opinion anyway, is this word abatic, the suffix abatic. It's too close to something else we've learned before this semester, that is diabatic and adiabatic. All I can tell you is don't get those terms confused. Diabatic and adiabatic is about moving heat into and out of air parcels, whereas anabatic and katabatic is about flow on a mountain. They're not actually that closely related of terms in terms of like their etymology and so on. Yeah, just don't get them confused, okay? The story as to why there's such similar terms is complicated. So let's go ahead and start thinking about the kind of flow that we would expect on a terrain feature like what I see in the background here. And we're going to talk about it in the example of anabatic flow. Anabatic flow, remember, is going to be our flow up the slope. To tell you the truth, I didn't much love the figure that was in your textbook. So I've scanned in a figure from that Stoll textbook that we sometimes swipe figures and readings from and so on. And the first thing I want you to notice about this flow is that it is another example of a thermally driven flow. In this case, it's going to be caused by the temperatures differences that are created during the day. You can see that sunshine on there and so on. Anabatic flows are upslope flows that happen during the day. Now, there's a lot going on in this figure. To make it a little bit more clear, I've colored in green what's supposed to be the mountain itself. There's actually two figures here. One's going to be showing something about potential temperature, and the other's going to be showing us something about the pressure field. The green is the mountain. That sort of stippled stuff on there is supposed to be like air flowing up the mountain. They're just trying to illustrate, you know, like kind of think of it as gray or something like that. That flow is going up the mountain. That's what that stipply looking stuff is right there. Now, like I said, there's two figures on this diagram here. Let's focus on the one on the left first. I'm going to hide the one on the right for now. Now, once again, there's a whole lot going on this figure. It would be best if we use our little magnifying glass tool and zoom in on just a part of this diagram right here. And what I see when I look at this diagram very closely, I see that it has contour lines on there. There are contours of, in this case, potential temperature. I don't know that the word will come up. I think it gets dropped once or twice in your book. The right word for a contour of potential temperature is an isentrope. That's in contrast to like a contour of pressure, which is an isobar, a contour of temperature, which is an isotherm, contours of potential temperature called isentropes. So I see that I've got some contours of isentropes of potential temperature on this diagram here that are just sort of coming from away from the mountain and then approaching the slope of the mountain itself. And what I want you to notice here, first of all, is that the potential temperature is increasing with respect to height in the vicinity of this mountain here. In other words, change in potential temperature with respect to height, partial theta, partial z, is greater than 0. Hey, we learned about that back when we learned about static stability. That means that this condition is statically stable. All right. Anabatic and katabatic flow are only going to happen under conditions in which the atmosphere is statically stable. If the atmosphere were statically unstable, if we started lifting these air parcels up the mountain, they would just rise on their own. They would form a thunderstorm and so on. That's not going to work. We're going to only work this to work against stability. Alright, so I've got this statically stable environment where the potential temperature is increasing with respect to height around my mountain here. Now the sun is going to shine on my mountain, warming the ground, and the ground is going to heat the air near the surface by a sensible heat flux, a transfer of stuff, namely joules of heat, per square meter per unit time. You can think of that as conduction. It's a little bit more complicated than conduction, but it's a good start as to what's going on there. And what that means is air that is actually in contact with the hill is going to get warmer than air that is slightly above the hill. So like, for example, I drew two little air parcels right there, right near the side of the slope of this mountain. See that one I labeled there in red? That air parcel is not quite touching the slope of the mountain. It's not warming up. It has the same potential temperature it had when it was farther away from the mountain. The other air parcel, which I labeled there in black, is in contact with the surface of the mountain, and therefore, because the mountain is warm during the day, it is transferring heat into that air parcel, and the air parcel is warmer. And that's why that isotrope goes between those two air parcels, right? The temperatures right along the surface of the mountain itself, the air almost in contact or in contact with the mountain, are warmer than the air a little ways away from the mountain, but at that same altitude. At the same height above sea level, the air is a little bit warmer and a little bit higher potential temperature close to the mountain than it is, if at the same height but some distance away. We have warmed the air along the slope of the mountain. Now, gosh, that sounds like a classic example of a situation where, the air parcel is warmer than the air around it at the same altitude, therefore it's going to want to rise. And so you would think, like I have on this diagram right here where I have 4 air parcels drawn, you would think they would just want to rise away from the slope of the mountain, and that would be the flow that you would get. But something else is going on as well. And to see that, we need to switch over to the other half of the diagram, which shows us what's going on with pressure. Now, the solid contours that are on this diagram here are contours of pressure. Now, weirdly, this book is using a weird unit of pressure called kilopascals. If you added a 0 at the end of each of the numbers on these contours of pressure, these isobars, you would get millibars. So like the one that's labeled 92 kilopascals, that would be 920 millibars. Or the one labeled 100 would be 1,000 millibars. I don't know why the book chooses to do that. Okay. That air that was right along the slope of the surface of the mountain that got warmed by a sensible heat flux, a conduction of heat from the surface of the mountain, the temperature isn't the only thing that changed. Temperature is a thermodynamic state variable that is related to all the other thermodynamic state variables like pressure and density. And in fairly complicated ways. We relate temperature, pressure, and density together in a fairly complicated, well, it looks simple, the ideal gas law, but in practice, very complex. It's very complex to figure out exactly what's going to happen when you change the temperature of the air with regard to how it's going to change its density and how it's going to change its pressure when all three can be changing. As it happens in this case, what happens is as the temperature increases, as that air is in contact with the mountain, its pressure is going to slightly decrease. So like if I zoom in here on my diagram on the right, and I look at each of those little isobars that are on there, those lines of pressure, I see that they curve down as they get close to the surface of the mountain, get close to the slope. So at a constant height, like what is at that dashed contour that's on there, that dashed line, we see that there is a higher pressure away from the mountain that gets lower as you approach the slope of the mountain at that constant height. In other words, there's a pressure gradient force. There is a pressure gradient force all around the environment around that mountain, pushing towards the mountain itself. So I have some vectors there illustrating the direction of the pressure gradient force. The pressure at any given altitude is a little bit higher away from the mountain than it is actually at the surface of the mountain itself. Well, that pressure gradient force is going to be acting on the air parcels that thought they were just going to rise away from the slope of the mountain, and instead you get flow that sort of hugs the surface of the mountain. It will flow along the surface of the mountain until it reaches the top of the mountain. We'll have anabatic flow flowing up the terrain until it reaches the top of the mountain. And if the flow is moist enough, as air parcels rise, you can get condensation and cloud formation and so on, producing a so-called anabatic cloud. So, like in this diagram here, it was surprisingly hard to find a good picture of anabatic clouds, but you can see this person admiring the terrain in the distance, and you can see how there's a cloud sitting on top of it. As air during the day was going up the slope of that terrain feature, It eventually reached the top, continued to rise on its own, and eventually was forming a cloud. Anabatic forcing like that can happen on lots of times, especially if you have like an isolated terrain feature. The classic example is the Black Hills of South Dakota. The Black Hills of South Dakota are some pretty surprisingly rugged mountains, but they're just a small area of them surrounded by plains in all directions. And during the day, air flows up into the Black Hills in the form of anabatic winds. And in fact, the rising motion associated with those air parcels as they flow up the mountain can form anabatic clouds or even anabatic thunderstorms. And in fact, raised areas of terrain like the Black Hills of South Dakota are good places to have the initiation of thunderstorms. That's really cool. Hey, and speaking of cool, let's talk about a feature that's all about how air cools, namely katabatic winds. Now, katabatic winds are another example of a thermally driven flow. They are being driven by temperature differences that happen. And in the case of katabatic winds, we're going to say that they happen at night. Okay, well, it might be more accurate to say anytime the surface is colder than the air. Because we're going to see that, like, for example, Antarctica. Okay, it might not necessarily be night. The sun might be up, but the surface of Antarctica is so cold. Okay, so it's going to be a thermally driven flow, and it's going to be happening anytime the surface of the mountain is quite a bit colder compared to the air that is touching it. Obviously, at night would be a good example of that, where the surface of the mountain has been giving off long-wave radiation to space, cooling, until it is now colder than the air around it. Now there is a sensible heat flux, transferring heat from a warmer object to a colder object. It's just now the warmer object is the air, and the cooler object is the ground, with the net effect of chilling the air. So air will be in contact with the mountain. It will cool by contact, by conduction, by, strictly speaking, by a sensible heat flux with the surface of the mountain, and get colder. And as the air cools, the air touching the slope of the mountain is going to get more dense. As air cools, it gets more dense. Again, it's a little bit complicated to sort out the difference between exactly what would happen with regard to temperature changing and density changing and pressure changing. But what's going to happen is the air is going to become more dense, and it's going to start, therefore, experiencing a negative buoyancy, just like we learned about when we learned about stability. And as that air is negatively buoyant, it will start accelerating down the slope of the mountain. So air will touch the surface of the mountain, cool, be denser than the air around it, and start draining down the slope of the mountain towards the valley. Sometimes you hear the phrase cold air drainage, or that this is drainage flow. As cold air drains down the mountain, a relatively warm air parcel touches the mountain, cools by conduction, and then becomes more dense and drains just by gravity down the slope of the mountain. Now, there are many, many examples of these kind of downslope katabatic winds, all of which have names. Some of these names, again, you may have seen in other classes about meteorology or something like that. You might have heard of Chinook surfins or Boras, just to name like three. You may have heard of Santa Ana winds, etc. These are all examples of flow going down the terrain under different conditions. There are subtle differences between a Chinook and a fin and a Bora, and I don't care, okay? That is not where we're going with this. I think it's more interesting to talk about a key word in that top box there, accelerating. You know, the air parcel, as it got more dense than the air around it, was now heavier and more dense than the air around it, and gravity began accelerating that air parcel down the slope. Okay, so it's negatively buoyant, it's accelerating down the slope. Funny thing about acceleration, though, as long as that acceleration is acting, that's what acceleration means. It gets faster and faster. So my flow is going to start at a slow speed down the mountain, but it's going to get faster and faster and faster as the air parcel accelerates downward. A constant acceleration makes a faster and faster velocity, right? Well, what's going to balance that? What's going to keep this thing from becoming a hurricane force wind as it comes barreling down the mountain? Well, a good answer would be friction, or maybe we'd say drag. I mean, this is by definition a wind at the surface of the mountain, and there's trees and rock formations and Lord knows what else, slowing the flow down. The flow will accelerate downward But the faster it goes, the more friction there is, the more drag there is, and at some point the flow will come to some kind of equilibrium where the acceleration just due to gravity of the air parcel downward, the acceleration of the air parcel downward due to gravity, is balanced by the force of friction slowing it down. In lots of sciences, that would be a good answer. That's a big part of the story, for example, of how a river works. Gravity is accelerating the water down the river, but the river doesn't get faster and faster and faster as it goes and then hits, plunges into the Gulf of Mexico at Mach 1. No, the speed of the river is a balance between the acceleration of the water down the slope and the drag that the water is experiencing with like the bottom of the river and so on. And in the same way, our flow is going to be kind of like that as it goes down the mountain. We're going to have a balance between gravity pushing the flow down and friction slowing it down. Now, to be honest, we may not actually even achieve that balance on a single mountain slope. I mean, look at these mountains here I'm working with on the background right here. The truth of the matter is the distance is just not that far. The distance between the top of the mountain and the valley, even on a really big mountain, is only a matter of kilometers. The truth of the matter is the air parcel will start moving down the mountain. It will be accelerating down the mountain due to its density difference. It'll have a negative buoyancy. But the truth of the matter is, at first, its acceleration will be greater than the friction, and it'll continue to accelerate downward. And the truth of the matter is, the air parcel might very well make it to the bottom of the mountain before it gets going all that fast, and there's all that much friction and so on. I'm not sure I would necessarily say that the flow will come to any kind of equilibrium coming down the slope of a single mountain. But a slope of a single mountain isn't the most exciting example of a katabatic wind. The coolest, no pun intended, example of a katabatic wind has to do with Antarctica. I don't know if you know much about Antarctica, but Antarctica is a big cold place that's just a big pile of ice. Underneath the ice, there are terrain features like mountains and valleys and stuff like that, but at this time in geologic history, Antarctica is just a big dome of ice. The ice gets down to basically 0 meters above sea level at the coast and is piled up quite deep in the middle. This diagram here shows approximately, just using colors, approximately the altitude of the top of the ice cap over Antarctica, and you can see that someplace kind of off to the right, not particularly close to the South Pole itself, but off to the right from there, is where the highest terrain is. And Antarctica is basically just a big dome after that. It just basically has a highest point in terms of its ice, and then the slopes away in all directions from there. And that's pretty far. The highest points in Antarctica are several kilometers up. It's a big terrain feature. It's a big piece of orography. It's a continental scale piece of orography. One giant, relatively flat, dome-shaped chunk of ice, high in the middle and low on the ends. Does that mean it's going to get katabatic winds? Oh boy, is it going to get katabatic winds. The katabatic winds of Antarctica are the things meteorological legends are made of. There will be very, very strong katabatic winds draining from the highest point of the continent down towards the shore. For one thing, the surface is incredibly cold. It's at the South Pole. 6 months out of the year, there's no sunlight at all to warm it all up. Even when the sun is up, the sun angles are very low. We don't get very much heating. The surface of the ice itself is very cold compared to the air masses that move over it from like the Southern Ocean, where the air won't be all that cold. Secondly, it's a really long slope from the center of Antarctica, from its highest point to the coast. Hundreds, maybe thousands of kilometers, depending on which direction you're going. There's plenty of time for that acceleration of that air parcel by negative buoyancy, by the fact that the air parcel has become more dense than, by contact with the ground, to be draining towards the coastline. So there's plenty of time, days of travel time for that air parcel to drain towards the coastline. Oh, but that's supposed to be balanced by friction. So it shouldn't really get all that fast, except for the fact that the surface is really smooth in Antarctica. There's no trees. There's very little terrain at all in terms of, like, I mean, there are a few places in Antarctica where the transantarctic mountains pop through the ice. In fact, that's what the picture in the background has been in this part of the presentation, is those are some of the transantarctic mountains. But in general, the surface of Antarctica has a remarkably short roughness length. As a consequence, since the amount of friction depends on the wind's speed, to get a decent amount of friction going, you got to get this wind really howling, hurricane-force wind, before you finally reach some kind of equilibrium between the gravity pulling the air parcel down towards the coastline and friction or drag. Near the coastline, these winds are often hurricane strength. And they're just a katabatic wind. They're just cold air draining off of the continent. You're an energy major. You know that what we really like is a really reliable, strong wind to go ahead and exploit. Boy, don't the katabatic winds of Antarctica sound like a great idea? Well, somebody beat you to it. This happens to be McMurdo Base in Antarctica, but all of the bases in Antarctica use, to a greater or lesser extent, wind power to meet their electrical needs. In part because it's difficult to get other sources of electricity. I mean, what are they going to use, solar? Yeah, no, not in Antarctica. You know, they also have diesel power, but they try to get as much of their power from wind power as possible. And as the environmental impacts of wind power go, Antarctica doesn't get much better than Antarctica. You don't have to worry about bats flying into your turbines or anything like that in Antarctica. Wouldn't it be great if we could exploit this commercially? Yeah, well, we'd have to figure out how to get it from Antarctica, you know, the electricity up to, you know, at least up to Australia or something like that, and good luck with that. Alright, we've learned about the katabatic and the anabatic flows of this part of the lecture. We're finally done with this lecture. Frankly, we're finally done with this module. Let's do a couple quick questions just to make sure you understood what you saw. Question 5. We would expect anabatic winds to be particularly strong on a day when it was particularly cloudy. True or false? How would cloud cover affect an anabatic wind? Make a choice from those two options and get a little feedback before you move to question 6.